go and get our slides back here. So hopefully you're out there somewhere. And we'll get underway. So I asked last week if you would share some of your pictures and what's home for you. And I got responses from 2 students, and I encourage others to please send me some stuff, and we'll share it with the class. Steve, I guess, lives in Kearney Lake, and this is looking off his patio, looking out over Kearney Lake. Kearney Lake, if you aren't familiar with Halifax, is sort of almost halfway, I guess, almost not quite halfway between sort of the peninsula part of Halifax and where the airport is. And I know years ago, once you left Bears Road in the main sort of peninsular part of Halifax, the highway out to the airport was just nothing but trees all the way until you reached the airport. That Kearney Lake was more cottages and that sort of thing. It's a good sized lake, very long, and I guess it can't be too windy or choppy because I believe there's still a rowing club that functions out there, so it must be smooth enough for rowing. Steve appears to have a very large patio out there, and it looks like a gorgeous view. And then we had Mudasim sent me a couple of photos, and one of them I'm presuming is his neighborhood in Dartmouth. Beautiful fall colors, very bright. It's been a gorgeous fall, at least on the sunny days. It's been very attractive. And he sent one other one, and that's hopefully you've seen St. Mary's before, but if you haven't, because of COVID, this is a photo that is relatively recent by the looks of it from the looking from the Loyola residence high rise out across the football field towards the rink, the student center, and the language center, library off there, and oh no, the library's out of sight. And in the distance, you see the downtown of Halifax. That I don't know. I haven't been on the campus since back in the spring sometime, I think, or maybe it was the midsummer. I dashed in to grab some materials, but haven't really been over there at all. Anyway, so what are we doing now? And please send me some photos of where you are, and particularly those people that aren't in Halifax, or be interested to see what a photo that makes you think of home when you see it. And so last time we spent 45 minutes or so going over assignment 3 and a very small amount of time on classification. And I think it was useful. Hopefully it really helped people understand assignment 3 and did better on it. I'm still marking one section of that class. But as I said in the class, with face-to-face classes, I'm always used to the class before an assignment due as being lots and lots of questions about, I don't understand question 1D, I don't understand question 3C, and so on. And we spend a huge amount of time going over these questions and helping people understand what actually is going on there. And there probably are more effective classes than me lecturing. And so I hope last Wednesday's class was useful to you. I still had an awful lot of emails afterwards. I don't know if it was people that were in class or other people that were there. Matt says very useful. Yeah. You should be getting after me. We've got 2 more assignments before that assignment's due. hitting me in advance saying, please go over certain things, or I'll try to hit you at the start to go over them. I anticipated with assignment 3, I went over it because I'd already started getting a lot of emails, and there were similar types of issues. And what was disturbing was it was people having trouble just getting started. So if you couldn't start question 1, how are you going to do question 3? That if you're not getting great grades, you should be asking me for help. Um, if you have asked me for help and you're still not getting grades, then okay, we've got a bigger issue. Um, but they, I know a number of the people that don't have good grades. I don't hear from them. They don't email me. Uh, um, so do that. If you're finding email is not effective, and it isn't really effective for a lot of some of the quick questions I can do easily by email, but some of the issues people are raising, we need a face-to-face meeting, and Zoom has proven to be effective for that. You can share your screen and that type of thing. They take a lot more time, and all of these, as I said, the volume of email that I get is staggering, but that's part of my job. And so don't, some students apologize for sending me too many emails. No, don't apologize. That you should be asking questions. It's always good. That, but the other aspect of it, though, is that many students seem to be dealing with an awful lot of issues. Um, some brought on by COVID. Others, though, it's just personal situation. Um, problems arise. That I've got you doing 22 activities this term. It's hard to keep track of. And I understand other classes have got activities every week, so there's a lot of things to keep track of. And I've had a few students that have missed a quiz, a test, whatever. They usually realize it the next day. We try to find ways of accommodating that and getting it sorted. Some have ran into problems with getting assignment 3 done by Friday, and we made some accommodations for that. So if you are in that type of situations, please contact me, and contact me early. I had one student contact me about a week after a test or something, and it just, why didn't you follow up immediately? But so I do. My expectation is that if you're running into trouble, you're going to contact me as soon as you know you're in trouble and may miss a deadline or may miss something, and then we'll work it out, and we should be able to find a solution. That um, okay. And so I'm into today's stuff. So because I zipped through things quickly last week, I'm going to go back over most of that again and try to put it all together. It's not a long class anyway. Classification, because we're not going to get into a lot of Excel stuff, and I'm giving you just a broad general overview and not getting down into the weeds. That it doesn't take a long time to cover the sort of concepts that are there. So just to make sure you're clear on what we mean by these classification problems, that value estimation, we take a whole bunch of inputs, stuff we know, and try to predict a number that we don't know yet. We've got some historical data on that outcome, and we've got historical data on the inputs, and we use that to do like you did in your assignment with predicting house prices. And so that you could build a model that you could predict the price of a house that is new, that's not part of your data set. And so we were predicting a number. In classification, we do the same type of thing, but now we're trying to predict a category. Are you good or bad? Yes, no. Most of the time it's a nominal variable. So these categories are just, they're different from each other. Maybe your program, is it arts or science or business? So they're just names. That most often, though, it's usually a binary variable, yes or no, and that's all we're going to be looking at. If so, the other type of categorical variable is an ordinal variable. And so there's a sequence to things. So I might be trying to evaluate risk and put you into a category. Are you low risk, medium risk, high risk? And we had a firm that some years ago that tried to build a model for us to predict the probability a student was going to graduate. And by that, we put them into risk groups of low, medium, and high. But really, those ones are very close to being value estimation problems, that we take that value and then categorize it. Sort of like when we did the financial example at the start anyway, I had you classify credit card holders as being low risk, medium risk, high risk. We just did it by grouping the ratings that these people had into different categories. So ordinal variables, it's categorical, yes, but it might lend itself to a sort of a value type estimation modeling. We're looking, and the clearest ones are to look at ones that are purely nominal and especially binary, yes or no, two groups. Which one do you fit into? And it presents us with new issues because we're trying to make good predictions, accurate predictions. Before, with your assignment, you were trying to predict a house price. Turned out we didn't predict it very accurately in that assignment at all. But their accuracy was how close can we predict it to the actual selling price? That can we predict within $5,000 or $10,000 of what a house is going to sell for? We were predicting it within $30,000, not very good. But this is different. We're still estimating an outcome and we're going to have errors, but the errors are different because either we're right or you're wrong. There isn't a size to the error. I wasn't way off. It was either you were good or bad. And but in most of these settings, these are not one-time decisions. That they are. It's like evaluating transactions, and we're evaluating billions of transactions to see if they're fraudulent or valid. And so we just want to know what percentage of the time are we right, and what percentage are we wrong, and that so we'd be having error rates of different sorts. And there are different sorts of them and they may have different consequences. But these rates may give us guidance and give us an idea if it is very good or not. That on the news this morning, there was a story about the airline industry trying to um, get countries to develop a common standard for testing passengers before they board an aircraft. And so since they're now developing these very quick tests of whether or not someone has COVID or not, the ones that you could get a result in, say, 15 minutes, then maybe we'd have it that at check-in time, you're administered this COVID test, and long before you board the aircraft, we'll know if you have a positive test or a negative test. And so then people would think that flying is going to be safer, and more people would fly. And, um, and that's what the airline industry would like us to do. But as the fellow uh, giving the story on the radio this morning on CBC said, but these tests are not perfect. They make mistakes. We'll be talking about that not long from next week or next class when we get into probability, probably. When testing things, that if you've got a test for COVID, uh, that it isn't 100% perfect. That the test results sometimes don't show someone is carrying the disease, and in some cases that it says someone tests positive, but they really don't have the disease. So we get what is called a false positive result. And the commentator was saying, well, even if it's 95% accurate, that we've got two types of problems happening. So these are the consequences of the choices. So if you use the test result to make your decision, that you may end up letting someone on a flight that still has the disease because we didn't catch every one of them. 1 in 20 people that has COVID will slip through and get onto an aircraft. That's still better than letting everybody with COVID onto the airplane. But it's 1 in 20 people that are carrying the disease and may not know it or trying to hide it are still going to be able to slip by. But the other thing that was being pointed out is that we'll get these false positives. And so here's a family going and taking a trip to see their elderly grandmother, and that one of the family members tests positive incorrectly, that nobody in the family has the disease, but one of them testing positive. What do? Do you send, uh, uh, you know, part of the family and leave someone behind? You let the parents go and one of the children leave one of the children behind? Probably not. How do you handle that? But what do you do when you have a false positive result? We'll actually talk about that later when we do probability. But it's trying to understand how classification and errors that you make is very different from forecasting a house price and being off by $5,000. That there are consequences to our choices, and they can be very different, and they can be quite serious. So, but we'll look at that a lot. We'll see a little bit associated with that when we do probability, and then later when we do evaluation, we'll be looking at that a lot more carefully. So last class, I introduced a couple of different strategies that you might take in terms of trying to do a classification. And there are many, many different types of strategies out there. One of the most common approaches is to start out by trying to estimate the probability someone has COVID, the probability someone has committed fraud, the chance of something happening. And then based upon that probability, making a decision. So if it's a 95% chance this person has COVID, then we'll make a decision based upon that. That they and we have it done in two stages or two parts. One is a problem of estimating a probability, and then we've got a decision rule. So if the chance it's a transaction is fraudulent is 60%, you'd probably reject it. What if it was 30% though? So it's more than likely a valid transaction. But if it was fraud, what are the consequences? If you reject it, what's the consequences? Maybe there's only a 10% chance that the transaction is for several $1 million. In that case, maybe I'm not going to, I'm going to do something else. Maybe I have an alternative to just accept or reject. But I need a rule to act upon that probability. And sometimes I'll be right and sometimes I'll be wrong. The decision rule, we'll look sort of at that when we're getting into evaluation, because there you're evaluating both the probability and the decision rule and how you work with that. Right now, if we're just looking at the problem of estimating the probability, it's estimating a number, that it's a chance of something happening. And that sounds like a regression question, a value estimation question. We just did value estimation. Why can't we just use regression for this? So, good question. It looks like it fits. It's got certain issues, though. That the big one is with the houses. You knew how big the house was, how big the basement was, how big the garage was, uh, how big the building lot was, a bunch of those things, and other characteristics of the house. And then you knew the actual price it sold for. So you had the input variables and the output variable price. This one has got a bunch of input variables, and the output variable is going to be a probability. But you don't have probabilities. You don't have historical information that is that this person had these characteristics, and then they had a 20% chance of having COVID or a 90% chance of COVID or that type of thing. They either had COVID or they didn't. So I'm talking value estimation, but the values I've got, it isn't a whole range of different numbers like probabilities from 0.001 up to 0.999 and everything in between. It's 0 or 1, good or bad, yes or no. And that makes it a lot harder for us to build it as a value estimation problem, because the outcomes, although our estimates may be probabilities and on a scale of 0 to 1, the data I've got for estimating my model of putting into the regression thing is just zeros or 1. So here's if I was looking at employees being classified as being acceptable or not, that and that these are people that are working for me now, and I know are they any good or not any good. When I hired them, I wasn't sure, and that the hiring process, having interviewed many people and gone through many resumes and reference checking and all that type of thing, it's a very difficult thing to do. So many of the people that I thought were going to be wonderful were total disasters. Others that I'm not sure about ended up being wonderful. So um, it's hard to do employee selection well, or at least I'm not very good at it. So suppose they, out of all the employees in the firm, and they may have hundreds of employees, they said, okay, identify 10 of them that were good employees and 10 of them that you wished you didn't have. And for each, we'll look in their files and see how they performed on 2 aptitude tests we gave them at when we first interviewed them. And one of them was one on their math skills, um, their quantitative reasoning skills, and one was on their verbal skills. And they're fairly common sorts of tests that are around. And so I've got these 20 observations. This is a snapshot of a piece of that spreadsheet, and I feed that into Excel, where my outcomes are just these ones and zeros. And Excel comes back with an answer for me. It's a bunch of numbers, it'll do it. And it came up with this model. Rating equals, got an intercept, it's got my 2 variables in there, slope values. I think it would be very hard to interpret these things. It gives me performance measures, an R-square. But as I said, we're not measuring things in the same fashion. I'd like to know how many good employees did it identify as being good and how many bad employees did it identify as being bad. So looking at R-squared and standard error, is that really telling me anything about how good it is? And even though I can do this, is it a good idea to do it? So uh, I encouraged you before with regression, look at the data. And so let's go back and look at the data. And here's scatter plots of our variables. I guess I could have calculated correlation coefficients, just a formula. So there's nothing to stop Excel from doing the arithmetic. But it's a straight line model. So I've got 2 scatters. Here are the employees I didn't like, and here are the employees that I did like. And these are their math scores. Similarly, over here is their verbal scores. And so the math scores of the unacceptable ones tended to be a little lower than the ones that were good employees. Good employees had better math skills. If I look here, I've got more, the high verbal scores seem to be good employees. Low verbal scores didn't seem to be very good employees. Well, it was a mix. So if they had a low verbal score, maybe I can't tell. But if they had a really good one, then they're probably a good employee. And I fit these silly straight lines. So I'm trying to estimate something like a probability, right? That was what we started out, and that's why we picked 0 and 1. And so is there a 50% chance, a 90% chance, a 20% chance this employee is good or bad? That's what we've got if you ride up and down this line. But this being a straight line, I can get the chance someone is good is 110%. You can't be more than 100% sure. How can you be 110%? Or down here, if an employee had a very low verbal score, then the chance they're good is minus 20%. What does that mean? You can't have a negative probability. It has to be between 0 and 1. Now, this one doesn't look as crazy as that one is, but so what's going on? Can I actively use this? Don't worry. Some of the methods we use are, if they work, use it. Don't ask why. Just if it's working, don't don't mess with it. And some of the methods are ones where you can't actually explain how it works. It's with the one called artificial neural networks. It's almost impossible to explain. I can't understand it at all. Um, but it comes out with predictions. Maybe we should just look and see how well does it perform. So I've just drawn this as, here's the actual rating. Is the employee a bad one or a good one? Here are the scores that it got, okay, from negative to positive here. So they're not probabilities. But if I decided the dividing line should be 0.5, halfway between 0 and 1, if that was where I put my dividing line, I'd have this group out here that good employees that I classified correctly as being good employees, and these bad employees I correctly classified as being bad employees. But I've got a bunch of bad employees that I'm going to classify as being good, and uh, here's 2 good employees I'm going to classify as being bad. So I'm going to make mistakes. If I move this line up, actually, if I put it just a little bit higher, like at 0.7 or maybe 0.65, then it would have classified all the bad ones correctly, but it still would have had problems here with these good employees would have been rejected. And we make these mistakes. We're going to look at this particular issue and use a similar type of diagram to what I've got here when we do evaluation. We'll summarize these results in a table, and it's known as a confusion matrix, which is a strange way of describing how you feel about the results of your method. How confused are you? Are you very confused? You're not very confused. But we'll get to that later on. The problem with, well, we had many problems with this model. Part of it is because the outcome is either 0 or 1. Okay. But if you accept that, one of the issues was that these things could become negative and they could become positive. We would like it so that our values would always be between 0 and 1. And one way of doing that would be to have a function that stays close to 0, then shoots up to 1 quickly, and then stays flat at 1. So it's got an S shape to it, like this. And this type of S shape depends upon how quickly it flips here in the middle. Is it goes up slowly like this, or does it go up and then rocket up very quickly and then go across? Which way works better? The This one looks like it would classify the bottom end correctly, the top end correctly, but these ones in the middle, it'll have trouble with. So that's with the math score. But maybe on the verbal score, which are a different set of scores, it might help us with these ones in the middle. And if we had other things, maybe they help figure out the middle. And so we can build a model that works. So how do we fit We did look before at nonlinear regression. We fit a cubic function to a set of data. And this has two twists like a cubic function, but a cubic would go and turn and go up over here, and over here it would turn and go down. That I'd like one that just stays forever in this fashion, and then forever as I continue that way it fits. And that always has that type of shape. And unfortunately, it gets to be very complicated when you go and flip it in that fashion. It's a function that's known as being a logistic function. Um, it's not to be confused with logistics of moving goods from one place to another, but that I don't know exactly the origins of this logistic regression name. You'll find it in most statistical packages, um, software that's designed for data mining and the like. You don't find it in Excel, although we can build a set of relationships and processes in Excel to go and do this type of work. I don't recommend it. That go and use proper software for this. And it involves a whole bunch of very complicated ideas to be able to fit it. Some trickier math than we would definitely want to get into in this course. So that is beyond what we're going to do. Just to show you what I mean by saying it's a messy function. It's a ratio of two exponential functions to estimate the probability. And it does have some simple stuff inside that does lend itself a little bit to determining what should be the right coefficients in there for those three B's that are there. You have to estimate them. And it can, with some work, be used for doing some causal analysis about interpreting what factors have what role in determining the likelihood or unlikelihood of different things happening. But it's quite scary to look at, and so leave a computer to do the work for you. I did do it in Excel, and here are my two sets of results. So here's what I had before. Here were the correct classifications there and the correct ones there, and here were my mistakes. When I used logistic regression, I ended up having more mistakes than I did with the simple one. It came out and compressed this. As you can see, it goes from 0 to 1. I don't go down to minus 0.2 or up to plus 1.2. That it does cluster things better in that regard of trying to classify them. And I can start thinking of the output as a probability. And a lot of people do treat it as a real probability. It just didn't work well with this example. But in practice, they work very well, and they are very widely used. It's one of the most common methods used for doing classification, is to first do this to estimate probability, and then from there they'll have a decision rule as to how to use that probability. But what I like about classification is you can start thinking about other ways of doing it, and pictures turn out to be useful for some of these different methods. So one that's been around a very long time is called discriminant analysis, trying to find a way of building a fence that keeps the good guys and the bad guys separated. So keeps the prisoners in the bad guys in jail and lets the rest run free. And so if I scattered my data, here the blue ones are the good ones, the orange triangles are the bad guys, and I'd like to build a wall between the two so that the good guys are on one side of the wall, the bad guys are on the other side. And rarely are we able to do that perfectly. We're still going to make mistakes some of the time. And as you can see, I've got all the bad guys on one side, so I did that right. but I ended up with two good guys being on the wrong side of the fence. And it's hard to do it perfectly. I've done this with a straight line, but you could have a curve that, say, came down and around and up again, and or came around this way. Maybe it came across here and across there and then down here. Um, I don't think there's any easy way to draw a simple line that would put these two values on the right side of the line. But I could have different shapes. And if I had more variables, it becomes a more complex spatial thing. But you've got the general idea. How do you build this fence in some fashion that classifies as many people as possible into the right category, that does the best job of doing that? And as I said, it's known as a discriminant function, and this one is called a linear discriminant function. But they can take on other forms. There's another one, and I don't. The math is messy, and I even have the concept is messy for me to get my head around, and trying to understand how you use the results of this thing. I just like it because it's a name. um, it's called a support vector machine. Now, what's a support vector machine? Um, it's just a tool for classifying things in computing science, and they talk of machine learning and artificial intelligence, a machine that can learn. So they talk of the tool they use as being a machine. So it doesn't look like a snowblower or um, a, a blender or a toaster or something. It is a machine, a set of mathematical uh, rules, and it uses some stuff from advanced mathematics. But as best I can understand the explanations of it, it's like trying to put a band through the middle, and ideally a very wide band, so there's big separation between the good guys and the bad guys. But I'm not sure exactly what you do with the people that get caught in the middle of that band. So it's a little more involved than that. But that's generally what it's called. But they give them these fancy names. One we won't look at is called, I mentioned it before, an artificial neural network. And it's supposed to replicate the way in your brain there are like electrical pulses between different bits in your brain. And can they replicate that to make good predictions? And they have a very complex way of going and doing these sorts of things. But it's a very popular technique, and it supposedly it works very, very well. Support vector machines supposedly work very, very well. Um, but they're very, very different from each other, and ones that are harder and harder to get your head around. That some of them just are simple rule sets, and we'll look at that after we've done probability, because probability will help us understand these rule sets. So it might be that if the math score and the verbal score are both really good, they're both above 350, then you're okay. But if your verbal score is low, I want the math score to be above 400. That and if you don't fit either of those, then I don't want you at all. But I'll have a bunch of rules that say if this, then this, if this, then this, if this. Otherwise, whatever. And how do you build those rule sets? Again, there's a whole bunch of different strategies, but we'll try to get some insight as to why they work or what they're trying to achieve after we've looked at probability. And it's easier than doing it right now. So there's a whole bunch of different ideas. That the one I want us to look at today is one that I find very intriguing because it doesn't really have a formula. Well, I presume it does, but I can describe it without talking about a formula exactly. And it reflects a lot of the way many of us make decisions. We make decisions based upon our experience. What do I mean by that? We try to imagine similar situations we've been in before. What did we do then? That informs, and did it work? Did it not work? That informs what the decision we subsequently make. And again, we've learned from our mistakes in doing that, but we're taking our experience and looking at trying to carry that forward. And so real estate is one. Real estate, estimating selling price. How much should you ask for your house when you put it up for sale? That how do you determine that? And it's not using the method we used in our last assignment. We don't put numbers into a regression formula. That some of the things we can easily measure, but some aspects of the price of a home, that there's the expression, there are three things important in the value of a house: location, location, location. Where the home is really dictates what you're going to be able to get for it. The best home in the world in the wrong neighborhood won't sell for much. An awful home in the right neighborhood, people will buy it. If you're um, in attractive neighborhoods in Halifax, unfortunately, we're seeing more and more older homes torn down because it's got the place has the right location, but the wrong house for what the buyer wanted, and they've got lots of money, and they tear it down and they build a new house, but they got the right location, and they're able to get a good price for their new house if they were to sell it because it's again in the right location. How do you build location into a model? There are ways, but it's more challenging. It doesn't easily fit into a formula. That what property appraisers do is they look for homes that they view as being similar, similar location, first of all, or type of neighborhood, maybe similar size, similar age, similar style, similar condition. Look at a bunch of those sorts of things, and that then they'll get, okay, it's approximately this amount of money. It should sell for about 350,000, but the kitchen is going to need to be renovated. The bathrooms are going to need to be redone. Those are important things, so it's not going to go for 350. We should ask maybe 330, something like that, because people are going to have to put a lot of money in to upgrade this home. But they're looking for ones that are similar to give them a starting idea, and then they tweak it from there. That and good appraisers are ones that can guess fairly accurately what the price is going to be. Then it's been interesting recently. There's been a real boom on real estate sales and people bidding up the price of a home. If they're bidding it up, then the initial asking price was too low because it seems several people want the house and they're willing to pay even more. So the market is telling them in the end what the price is. That although this is subjective, requires a lot of knowledge, it is an interesting concept. Find similar situations and see what happened in those similar situations. And from that, build your classification. And so it's whether that be looking at employees that had similar characteristics on time of interview and what eventually you saw happen with them, and or it's similar transactions that you've seen before and what happened to them, that were they fraudulent or not, and that from there try to do the classification in your the text material for this in chapter 8. I think at the end of it I've got a story that Nate Silver tells. Well, it was being, well, from him, but someone else was retelling it. Nate Silver is the fellow behind the website 538, which is, I think, most view as being the best political predictor website of outcomes of US elections. Um, all kinds of media outlets are now referencing it as the election comes up tomorrow. It's also a very popular one for sports, And he tells the story of the Boston Red Sox a decade ago trying to make a decision on whether or not to keep Daniel Ortiz or let him go because he was in a slump, and how they could analyze that by looking at similar players in the past that had slumps and see what happened with them. This type of method of looking at similar goes under the name of KNN. K is how many past cases you look at, and the NN stands for nearest neighbor. So these are ones that are close. Find the nearest neighbors to the one that you're looking at. And there are a lot of methods we use in other types of problems where we use nearest neighbor rules. And I'll make reference to that in a minute. So here's graphically, this is the same sort of picture we used a minute ago for a discriminant function and trying to decide how do you split them. Instead of giving you a formula, I'm using this for prediction. So here are 20 cases summarized here. So I could go and pinpoint a new case on this. So suppose I've got someone with a math score that was 390, but their verbal score was only 340. So that's sitting in the middle of my diagram here as being my new case. Right close by are two bad employees. Not far away is another one, but not far away is a relatively good one. And over here is a good employee. Over here, I got two others. If my rule was look at the seven nearest neighbors to my new case, and base my decision on the seven new neighbors. And how did they work? If I look at it, well, out of the seven, I got four that were good. So if I was to choose, is this one going to be good or bad? Maybe I'd say this one's going to be good. Someone else may say, yes, but the three closest ones were all bad. So the ones that were most similar were bad ones. So shouldn't the distance there have some sort of role? How do you measure closeness of these neighbors? And so then we have to start looking at what do we mean by closeness, and how do we define similar? And the when this sort of material is presented in a lot of introductory books, and they talk about the closest ones and nearest neighbors, and they have the picture like this, and they all use a diagram like this, and have a spot and little distances that run out. And this term nearest neighbor, I said we use it for other types of strategies. Nearest neighbor is probably best known as a popular strategy for routing delivery trucks. So if you're a person doing deliveries for Amazon or whatever package deliveries for around the city, and you see lots of that now because so many people are ordering their products online, that the driver, when trying to decide, okay, which location do I go to next? Go to the nearest one. Go to the nearest neighbor to where you are right now. Go to the closest one. And then after you make that delivery, go to the closest one. And then the next one, go to the closest one. Generally, those methods actually work quite well. And they're really simple because you don't have to do a whole bunch of planning in advance because your choices of routes can be all over the place. But this is a very simplistic sort of method. It doesn't always come up with the best route, but it generally comes up with a very good route. But think about how you're measuring distance. Okay? In those ones, we measure distance in one of two ways. And I think of this with nearest neighbor methods. Depending upon how movement of goods is taking place, I may think of it if it's long distances, like going from city to city, town to town, then I might use straight line distance between the 2 points. But if I was making deliveries in a city, then our streets, many of them go north-south and others go east-west. And so to go from A to B, I've got to go north for a certain distance, and then I got to go west for a certain distance. And so maybe I should measure distance in what we call road distance or metropolitan type distance. There are different distance measures that um, with those routing of trucks cases that not only did sometimes you'd look at with some cities at uh, the road distance, but you'd treat north-south differently from east-west because the traffic flow and the ability to travel quickly. Sometimes the major arteries all go north-south, and you can travel very quickly, but if you're going east-west, it's much slower. So maybe we have to adjust for travel time, not just distance. So how are you measuring this? Is it time? Is it distance? Are you trying to approximate it? Well, that makes sense when I'm measuring closeness as if I was measuring distance. But we're measuring similarity. Means, same sort of idea. But think about it though. If you're looking at two customers, are they similar to each other? Some of the measurements are numbers, like distances, like ages or income or education, but they have different units. How do you measure uh, so many years north-south and so many $1,000 east-west? Because those are the different measures that you've got here. How do I combine those sorts of things? How do I standardize my units? That what do I do with gender? Um, or ones that I'd classify as strictly categorical. How do I measure closeness? Are you almost male or almost female? That are you almost in business or almost in arts or almost in science? Um, are you in one program or another? That uh, do you are you may almost going to renew your cell phone plan or you're not going to renew it? Yes, no. What do you do with categorical variables? There are lots of different sorts of things you may want to throw in there that are going to make measuring distance awkward. That they, and then you've got to ask yourself, how important are the different measures? Being really close on age, but being very different on income, do they balance each other out? Just looking at the two variables, are income and age equally important? I don't know. This is getting messy. How many neighbors should I look at? Should I look at 3, 5, 7? Generally, the more cases we look at, the better our decisions are. Okay. That more data is better than less. Let's go back here to our picture. So if I made it based upon the nearest 2, I'd make one thing. Here's the nearest 7. That's still not very many. Suppose I wanted the nearest 12. Well, I'm capturing probably all, but or it's a huge group I'm going to have. That as I expand the number of cases I use so that I've got more information, I'm looking at cases that are less and less similar. I've got to go further and further away. So that, yeah, you've got more information, but is it good information? So a small number is, at least they're better than big ones. That quantity versus quality. A lot of people like to pick odd number of cases so that we can break ties. So it's 4 out of 7, 2 out of 3, that type of thing. I don't get a tie, and then how do I break ties? That the you may have challenges when you go to justify your recommendation. That why are you picking this? And it's you don't have this formula or fancy technique. You're just finding a bunch that are similar, however you measure that. There isn't a same sort of formula like you do with regression. And people like formulas. They seem to trust them more. So you may have trouble on that. That you need to have a whole bunch of old cases because I'm looking through my old cases to find 7 that look like this new one I've got. So how many do I need to keep in my old data set here? Thousands, tens of thousands, hundreds of thousands? How big should it be? The bigger it is, the older they are. And should I really keep the old one? So I've got a trade-off there. And I want still, though, a large number to pull from so that I can find, more likely I can find ones that are very similar. But how many should I keep? And one of the challenges here is with regression. In fitting a regression model, if I had a huge amount of data and I fit my model to it to make my predictions, and the more data is the better. But when I'm finished, I just have a formula. So I have a formula for house price, and I put in the number of square foot of these, and the age of the house, and all these other things, and I get a price out. With this one, I've got to keep all that data because I have to go back to the huge data set to find those ones that look similar. So some don't like it because you've got to keep saving a lot of old data to dig through. And there's so many characteristics you could look at. You could have all kinds of information on those past cases. How many different things do you want to look at? There's so many choices you have to make. And there are others beyond what I've raised here. This sounded simple at the beginning because it does reflect the way we make a lot of our own decisions in our head. It's based upon how did we handle a similar situation previously and were we successful or not? If we were successful, we used the same approach we did last time, maybe adjust a little bit. If it was unsuccessful last time we used it, we might try changing our approach and making a different decision. That, but this is very, very complicated. That despite all these challenges, this method has been very successfully applied. And you can imagine different people with the same data set would approach it quite differently because they define similarity differently. And so we could have a whole bunch of different similarity models. There isn't just one because there are different ways we could have measured things or weighted things. But there are lots and lots of very successful applications of this. I like it in particular because it's a different way of thinking about how to solve a problem. And I like people that are open to other types of approaches than always using the same approach. So I've showed you some of the many, many, many different methods that are out there that I've only have limited familiarity with a handful. And but this is a very, very common data mining application, probably more common than value estimation. And there are many different strategies. And here we've identified 3. 1, build a formula to estimate probability, then have a rule. 1, build a fence that separates the good guys from the bad guys, that can discriminate between them. 3rd one, look back for other cases that look similar to the one you've got right now. And what happened in that situation? And use that as your guide for your future. Very different ideas on how to do it. That there isn't a best method. We'll later on look at 2 others. One that's based upon probability and ideas from it. The other one that's I find informed by probability. It doesn't explicitly use it as much as the other one does, but it helps in terms of the reasoning and thinking. It's a rule-based approach, but all of these different ones have been successfully applied in specific settings. Some people have advocated that you should try multiple methods, that take your data set, split it, use one of them for estimating and developing everything, like we did with regression or whatever, and then use the other one for testing. So after you've built your model, you've come up with your rules, you've defined how similarity is going to be and how many cases you're going to look at and all of those sorts of things, and you think you've got a good strategy. Now go and try it out on this experimental group and see how well it performs. You have another one that's based on logistic regression. You've built a formula, okay, and you've got a rule to work with. Go and try it. You've got one that's a discriminant function. Fine, build it. You've got it all worked out. Let's try it out on this new group that we haven't looked at before. So each one we try out on new data that we have not used to do the training on and seeing how they perform. And whichever one seems to perform the best, maybe we pick that one. Maybe we find certain methods work best on certain types of cases we can classify. So we're going to use all the methods. We're going to say if it's this type of problem, we'll use this one. If it's this type of problem, we'll use that one. All kinds of strategies. Too many. Too many makes it confusing. But there's no right answer. The next two classes I'm going to do probability because I need to understand probability to evaluate my classification scheme and really understand what I referring to as error rates and what do those error rates mean. How can I wrap my head around probability and risk? And it is very difficult to do. We don't understand risk very well at all. So first off, we'll try getting the basics with probability. Then we're going to spend a week looking at some methods that probability might suggest as being other strategies for doing classification. Then we'll go and look at evaluation that we could apply to any strategy. And how do we evaluate whether or not a classification model is performing well or not performing well? And that will be almost at the end of the course then. We've only got 4 weeks left, I think, something like that. And that's it for today. So I hope that's useful, and you take care. You can see me again on Wednesday and get after me if you've got questions on anything, if I can help you out in any which way. Take care. Bye now.